Here are the notes that we looked at concerning compound interest, and we started out looking at how simple interest here in example 1 compared to compound interest. So we took our scenario, calculated the simple interest, and then using our recursive idea, we calculated the compound interest of that $1,000 investment and saw that when you compound interest on top of interest, you actually gain a little bit more, and we got that $1,025.25. So a little bit extra interest because of that compounding. And from there, we created two formulas. One of the compound interest formula just uses a capital N to represent the total number of compoundings. And the one that I like to use most often, that exponent is N times T, where N is the number of compoundings per year, and then time is in years, and you can multiply that out. So we use that formula to figure out example number 2, the prepaid college fund of $15,000. If it earns 4.5% interest and is compounded quarterly, so remember that's when N is 4, for a total of 18 years, what's the future value? So using our formula, we saw that it was about $33,566.48 there. But this is the type of problem that we can now start doing on the TVM solver in our calculator, TI-84. And that was example 3. So looking at all of the different components of the TVM solver, where the capital N is the total number of compoundings, so that again is N times T. If you can't do that in your head, you can just type it into that spot, 4 times 18 in this case. The I% is the annual percentage rate, so we can call it R, but it's not turned into a decimal, it's just kept like 4.5 instead of 0.045. Present value is your principal. Payment is the periodic payment, and for this problem it's just 0 because they're not making periodic payments. They just purchased a lump sum of $15,000. And then the payments per year and the compoundings per year, we said that those are always going to be the same. And so in this case, since it's quarterly, they're both going to be 4. For now, we said just leave the payment to the end, and I'll explain that a little bit when we look at our annuities. But for now, just keep that on end. The other thing to keep track of when you're entering in the values for either the present value, the payment, or the future value, we said if money is flowing away from you, so it's like you're making a payment, that is going to be a negative value. If money's coming back to you, like you're getting a loan for a car and you're gaining that money, that's positive money. So just kind of keep track of whether things are positive or negative. So on the same problem from previous, we entered in all of our values. To solve for future value, we hit that alpha solve, which is alpha enter, and we get the same value, $33,566.48 there. From there, just to show one thing too, so the present value is negative because the grandparents had to give that money away, and then it earns interest, and the future value is positive, meaning that money is flowing back so that Jim can use it for whatever, education or some other reason. So on example 4, we saw how nice it is to use the TVM solver to solve for various pieces of a problem like this, in that this part A, we solved for the interest rate. On part B, we solved for the future value like we did just previously. But you can also solve for present value. You can solve for N and figure out the time. The only thing that you can't use the TVM solver to solve for is the N, the payments per year or compoundings per year. You can't solve for that. But all of the other values you can, and we saw that the TVM solver is a lot easier to solve for than if we had to go back and use our formula to either solve for the future value, the payment, the interest rate, or the length of time. So a lot of advantages using that TVM solver. Now the problem with this example that we looked at in class was that most people can't just take like $22,000 and put it in a savings account and wait 18 years. That's not a very convenient way to save money. A more practical inconvenient way to save money is if you put in a little bit periodically, like every month, put in $100 into a savings account. Or if you have a job and you get 2 paychecks per month, maybe take a little out of each paycheck and deposit that into a savings account. So that'd be twice a month or 24 times a year. And when you do periodic payments into a savings account, what that is called is an annuity. So an annuity is like a savings account where you make small periodic payments instead of one big huge lump sum. Now, if we look at the formula for what an annuity is, what the annuity formula looks like is the future value is present value or principal, so PV, times 1 plus R over N to the NT minus 1, all divided by R over N. And you can see some pieces of this, like our compound interest formula that we just looked at. That's the PV times 1 plus R over N, but there's a couple other pieces added into it. It's the minus 1 here and the dividing by R over N. But that should look kind of familiar because back when we did the sum of an exponential sequence of numbers from our last unit, we saw that the sum n is equal to, back then we said, well, it's the initial value p sub 0, but that's like our present value over in our other formula, times 1 plus r to the n plus 1 minus 1, all divided by r. And you can see how similar this is. Here you've got the 1 plus, this is periodic interest rate, r over n, to the nt. Here is the 1 plus r. The big difference is n plus 1, and maybe I'll explain why in this formula it's n plus 1, and in our annuity formula it's just n. But they both have a minus 1 and then divided by r. Minus 1 divided by that periodic interest rate, r over n. So they're very similar. And this is because this is really adding up periodic payments. Every single month we're adding in a payment, but we're getting interest, similar to adding up that geometric series there. So let's take a look and see how we can use our solver to solve this particular problem. So it says the Dixons want to save for a down payment for the purchase of a house. They figure they can save $350 each month, so that's, let's say payment is $350 each month. And they found an account that pays 3.75% APR, so R is 3.75%. The APR is compounded monthly, so we know that N has to be 12. And part A says how much can they save in 5 years. So you know that that's T is equal to 5 years. Now it says assume this is an ordinary annuity. So what does that ordinary annuity means? So this is where we can start to look at what is this payment down here, this payment, and why do we have end and a begin. So the difference is the end here, this is when you make the payment at the end of the period there. So let's say it's March. You don't put your money in on March 1st. You make your payment at the end, so like March 30th there. So that's making the payment at the end. The begin is when you make the payment at the beginning of the period. There. And when you make the payment at the end, this is what's called an ordinary annuity. So ordinarily, we do make the payment at the end. When you make the payment at the beginning of the month, that's actually called an annuity due. So it's due at the beginning of the month, which is pretty rare. So that's why we probably won't ever use that one. But when we assume it's an ordinary annuity, we'll always put it at the end of the month. If it's not said, we'll assume it's at the end of the month. We would have to be specifically told that it's an annuity due in order to know to check that begin part of the TVM solver. So let's see how we can set this up. The total number of payments, capital N, is N times T, so 12 times 5, or that one we can do in our head, 60 is what that would be. Interest rate is 3.75. The present value, well, let's assume that they don't have anything in the bank to start out with, but they could. They might have a couple thousand already in there, but in this case, let's just assume they don't. The payment is $350. Now, since they're giving that to the bank each month, that's going to be a negative $350. Let's see, we're going to solve for the future value because we want to see how much they're going to earn after those 5 years. And then the payments and the compounds per year, again, are 12 each on those. And when we go back up and solve for our future value, we get 23058.30. So it looks like they're saving about $23,058.30 there. So not a bad savings for the down payment of a house. Part B says, how much interest did they earn? So out of that $23,058, how much of that was really interest? Well, what we need to do first is calculate what were their total contributions. How much did they actually pay into the account? So if I go total contributions, let's see, what did they do? They made 60 payments of $350. So their total contribution, 60 times 350, is $21,000. So yeah, it looks like about $2,000 was in interest, but we can actually calculate that. The interest is going to be what's currently in the account, $23,058.30 minus $21,000, and we see that the total interest that they earned over those 5 years is about $2,058.30. So not bad, gaining about $2,000 of free money, but it's not free because you kept paying into it. But that was their interest that they earned. So that's what an ordinary annuity is. And we'll look at a couple other examples here from the notes.